Reflection of waves. What is reflection? It is the bouncing back of the wave in the same medium from where it comes. Let me show you. If here is a wall and here is a rope, this is a wall. In terms of wave, we say it a boundary, and here it is a string, a tight string, so that it is having some tension. It can carry wave with it, and one person is creating some pulse. It is called a pulse, and it is an incident pulse which is moving in this direction. When it strikes here at the boundary, it gets reflected here, and here the boundary is fixed, so there is a 180-degree phase shift in the pulse. Dear students, the boundaries are of two kinds. One is the open boundary and another one is the fixed boundary. First we shall see the fixed boundary. As I've already shown you that when the incident pulse and the reflected pulse have 180-degree phase shift, then it is called a rigid or a fixed boundary. So there is a 180-degree phase reversal. Then next comes, what is the equation of incident wave? We already know yi is representing a incident pulse, and here a is the maximum displacement sine kx minus omega t. K is the wave number, x is the direction along which the wave is traveling, omega is the angular frequency, and t is the time. Dear students, kindly note that when the wave will be reflected, the amplitude is remaining the same because there is no energy losses. We are assuming k is the k is the wave number, and x is already there. Here, for the reflected wave, when the wave is returning back and is moving along negative x-axis, we'll write here plus sign instead of minus, and omega t is as it is plus phi, because here the reflected wave suffers 180-degree phase shift. If we will solve, sine 180 plus pi is equals to minus sine theta. Sine 180 plus theta is minus sine theta. So the reflected pulse becomes minus a sine kx plus omega t. Dear students, remember here plus sign indicates that the wave is traveling along negative x direction. Here minus sign indicates that the wave is traveling along positive x direction. Let us move ahead. This is the figure of reflection of wave from the rigid boundary. Here the pulse is moving, coming towards the boundary, and the moment it strikes the boundary, it gets reflects back, but it suffers 180-degree phase shift. Now let's move ahead with the next, open boundary. Open boundary figure is something like it is a rope, and here we are having a rod, and this rope is connected to a ring which is inside this rod. So if someone creates a pulse, this ring will also move up. Okay, this ring will also move up because the rope is tied with this ring. So what happens during reflection, the ring comes down, it will transfer back the pulse in the same phase, so there is no phase change during reflection of incident pulse from a open or a free boundary. Let us see what are the equations governing this reflection. As we already know, the incident pulse is represented by a sine kx minus omega t, and the reflected sound, not sound, actually it is a pulse. Sound wave is not something we are representing, we are recording the incident pulse. So a amplitude is same. Now here sine is as it is, only there is a direction change because there in the incident it was traveling along positive x-axis, and here it is traveling along minus negative x-axis. So here for negative x-axis we represent here by plus, and for positive x-axis we represent here by minus. Okay, now let us move ahead with the next topic, which is the stationary waves. They are also called as standing waves. Stationary waves are produced when two identical waves of same frequency and amplitude but they are traveling in opposite directions and they add with each other. For example, we are having one rigid boundary and there is one pulse, and when this pulse adds up with the another pulse. Let me draw the figure again. This is one reflected pulse and this is one incident pulse, right? This is incident pulse, and this is reflected pulse. Actually, continuously we might increasing the incident pulse. So here what happens when they adds each other, what will happen? They will create superposition addition, and when this boundary is also fixed and this boundary is also fixed, so what will happen? There are few such kinds of the pearls. When they adds each other, there is some kinds of a stationary wave is created, right? So stationary waves is something like it's not transferring energy from one place to another, okay? It is trapped between the nodes is something, दिस पॉइंट इज नोट बिकॉज इसके बाद वेव ट्रेवल नहीं कर सकती. और दूसरी बात कि यहाँ पर दिस पार्टिकल कैन नॉट मूव अप एंड डाउन. Okay, this particle cannot move up and down, so it is called a node. Here also this particle cannot move up and down, so here it is called a node. Here it is also called a node. Node is a point which cannot move, where there is no displacement, and for node and for no displacement point is called a node. No displacement point is called a node. So what is happening here? Some particles are suffering maximum displacement, which are called antinode, and some particles will not suffer any displacement. It's called a node. Now let us move ahead with the details of this chapter topic. I have already mentioned here the points of zero displacement are called node. These particles are perfectly still because of the permanent destructive interference, and the points of maximum displacement are called antinodes, and they vibrate with the largest possible amplitude because of the permanent or constructive interference. I hope it is clear to you. And you will study later that the distance between two nodes is lambda by 2, and distance between one node and one antinode is what, lambda by 4. Actually, you will have to learn it. You will also going to see this in the upcoming slides. Here we will start. I have already discussed this point. Here we will start the standing waves in a stretched string. So as you can see here, this is one string fixed at one end, and this is another end which is also fixed. So there are the three conditions, okay? If let us suppose there is one wave which is produced, and this same wave gets reflect back, and after some time what happens, the particle try to adjust something like only one loop is formed. Okay, it's not a one wave, try to remember. It is something like many adjustments. After some time what happens, particles try to adjust, and finally few particles are suffering maximum displacements, and these are the particles which are tied to the wall of this walls, so they cannot move. So these particles are called nodes, and the particle which is suffering a maximum displacement is called antinode. When this situation occurs, this is called fundamental harmonic, okay? And when there is some situations that, for example, here there are two loops, so it is called a second harmonic. And when there are three loops, we are saying it as the third harmonic. Now let us see the conditions when these are produced. Actually, something like the figure here, let us see here. For example, if it is a string and the string is being pulled, and there is some kind of disturbance is produced, and the way this kind of disturbance is produced and they adds each other, finally this kind of pattern is being produced, right? This is called a fundamental harmonic. And let us suppose if some person try to touch this point lightly, then what will happen, again a node will be formed here. So these particles will adjust something like, यहाँ node बनेगा तो बीच में एंटी नोड और बीच में एंटी नोड बना लेंगे, there will be two loops. Then यहाँ पे this is called second harmonic, right? Okay, let us come back. In the first harmonic, let us suppose the length of the string is L. इस रस्सी की लंबाई L है, if it is L, and only one loop is formed. The particles are vibrating such that few sets of particles are always suffering maximum displacement called nodes, and few particles are bound to not to move are called node. Then only one loop is forming, then it's called a fundamental mode. And the whole length is having only half wavelength. See dear students, this is one wavelength. Okay, but here in the fundamental mode you are seeing only one half, because another half will would be completed after it, but it is bound to vibrate. L length is bound to vibrate in half length, so it is called fundamental harmonic wavelength. Okay, just cross multiply lambda and frequency value, speed upon wavelength. This is the formula of frequency. Similarly, we'll see the second harmonic. Second harmonic is nothing so magical. It is something like it is a wave here, and wave was there. Okay, see, some person touch this point also. Now particles will adjust vibrating, something like there will be a node here, there was node due to boundary, there is node here due to boundary, and here the particles are having antinode. So the whole length is having one complete wavelength. One complete wavelength, it's called, it will make us, it is called a second harmonic. And if you try to find out the frequency here, frequency is equals to speed upon wavelength. Wavelength is L. So if we compare this with the previous one, which was v is equal f1 is equals to v upon 2L, if we compare, then we find that the frequency of second harmonic is twice of the frequency of first harmonic. It is also called the first overtone. Similarly, we are having the third harmonic. There is no need to go in too much of the detail. Third harmonic, something like there are three loops being formed. So three loops, this is one half, this is another half, this is third half. So in one complete length you are getting three halves. So cross multiplying, get lambda is equals to 3. This whole string length is L. Frequency is something like speed upon wavelength. Wavelength is something 12 upon 3. It is thrice of f1. So frequency of third harmonic is thrice of f1. It is also called second overtone. These are the another names of third harmonic. Now this part is finished. Let us move ahead with the next point, which is the closed organ pipes and the open organ pipes.